Today's speaker is Robert Hargraves. He's going to be talking about power from thorium reactors. I should give you a little introduction to Robert Hargraves. He worked at Dartmouth and eventually started a company called DTSS, which was intended to promulgate some of the software that he and others had written while at Dartmouth on one of their first time-sharing systems there. The time-sharing system that he worked there was actually the one that Bill Gates ended up learning BASIC on, which is sort of a somewhat irrelevant to Bob's later career. Bob has a PhD in high-energy physics. About 18 months ago, he started teaching about nuclear energy policy at Dartmouth. And during the teaching of that course, he found out about liquid fluoride thorium reactors. And they have a number of nice properties. And since then, he's been singing their praises. And that's what he'll be doing today, hopefully. So I think I'm going to turn it over to Bob. Here you
go. Thank you. You all know we have an energy crisis and a climate crisis. We have 300 parts per million CO2 going up. We have the cost of oil going up again, and so on. We import $350 billion worth of oil from the unstable Middle East. So we have a lot of problems, and sometimes it's easier to step back and see if there's a wider solution to all these problems. So today we're going to talk about some of the people who've noticed the limits to growth in the past, the concept of what I call aim high, try and solve a really big problem, an answer that I believe might work, thorium power, a project, and a question period. First, we talk a little bit about global warming, and you're also familiar with it. I'm not going to dwell on it except to say the polar bear is the poster child, but we have more to worry about than drowning polar bears. We have the problem about the cold polar seas retreating to smaller and smaller territory, those seas being so important for the development of algae that are the source of life in the sea. We have the problem potentially of the glaciers melting in the Himalayas, which are necessary to even out the water flow to the people whose lives depend upon the food that grows there, hundreds of millions of people. We have desertification. We have problems with, even today in the Amazon rainforest, the rate of forests being cut is as much as 3 times as it was a few years ago, partly driven by the need to farm more biofuels. We have the problem about fish in the ocean. 40% of the large animals are stressed and probably beyond the point of recovery. I believe we have only a few more years of tuna. The Japanese have created a strategic reserve of tuna fish by allegedly harvesting illegally off the coast of Australia. And last but not least, we have air pollution. We have particulates, 2.5 microns and less, emitted by coal power plants that are responsible for the deaths of 24,000 people a year in the US, hundreds of thousands in China, and according to the UN, perhaps 2 million people worldwide. So we have plenty of problems to deal with. Dennis Meadows came to Dartmouth years ago when we were there, and I actually helped attract him to Dartmouth because I managed to get Phil Koch to write the Dynamo compiler in timesharing to get him to come and move his research to Dartmouth. This is a graph that came out from an old pin printer, multicolored ribbon teletype, cost $5,000 at the time, and it's here partly for historical interest. His projection over the couple of centuries on the graph is resources being diminished, food supply going up and then crashing, industrial output the same, pollution rising indefinitely, and finally population in his projections rising and falling. The limits to growth was sponsored by the Club of Rome. It was disparaged at the time as being unrealistic because in past history, people would say every time there's a a lack of something, technology steps in to fill the void. But today we begin to think that, well, growing population in a finite Earth is perhaps a problem. Here's the population projections for the world. 6.7 billion people now, and we're blithely told that the population of the Earth will rise to 9 billion by 2050. I personally think that's not likely to happen, and for bad reasons. But if you look at the OECD nations' populations and the US populations, you see the rate of growth is not nearly the same. So I got interested in how prosperity works with population. I went to the CIA databases that are online, and they track children per woman for various countries and GDP per capita as an indicator of wealth. I then sifted out only the nations that had populations over 10 million people and just looked at the result. The stable replacement rate for a population is about 2.2 or 3 children per woman. And you notice quite quickly that all the countries that have the largest population growth, the largest fertility rate, are those that are the poorest. So I kind of looked at that graph and I said, let's invent a concept called modest prosperity. And I just sort of arbitrarily drew the line at about $7,500 per year GDP per capita. And if you look there, the nations that have that level of prosperity generally have much lower birth rates. They have stable birth rates. There are only 4 outliers in that graph. The most outlandish one being Saudi Arabia, that has both wealth and children. Now, prosperity also depends on energy, but it depends on other things too. It depends upon the rule of law. It depends upon food, shelter, medicine, a stable financial system, and a government that does not oppress the people badly. But energy is a good indicator, and electrical energy is a good indicator of the prosperity of a civilization, because the electrical energy is necessary for water, for purification, for septic processing, for manufacturing machinery, for transportation, heating, refrigeration. Electric power is important to prosperity. Here's a graph again from the CIA data that I could find. Kilowatt hours per capita per year on the horizontal axis, and GDP per capita going up. And I just sort of sketched in a line here trying to emphasize the fact that these seem to be pretty strongly related. The US number, by the way, is somewhere around 12,000 kilowatt hours per capita per year, and somewhere around 45,000 GDP per capita. But if we look at that prosperity number on this graph again at $7,500 a year, that seems to indicate that somewhere around 2,000 kilowatt hours per capita per year is a kind of a break point. If we could get to that level of energy use, perhaps these nations could become prosperous enough to keep their populations under control. Now, but let's look again at the developing nations and look at what's happening. They want to increase their energy use because they want a lifestyle similar to the lifestyle in the US and other OECD countries. And they're going to do it with coal. Coal use is growing in all of these countries, stable in the US, increasing in China and India and the rest of the world. So unless we do something different, the developing nations will burn more coal. A common thought is that conservation should solve this problem here in the US. And people like Amory Lovins think of negawatts, the concept that if we could save money, we wouldn't have to build new plants and so on. In fact, the DOE is projecting energy growth. I'm hoping we can hold it flat. I know the Google.org projections show an expectation of controlling energy growth. And in fact, in the last quarter of last year, energy use, residential electrical energy use, actually did diminish a hair. But let's just take an example. The US uses 3.8 petawatt hours of power per year in the US. And let's suppose that we were optimistic and said we wanted to cut our energy use in half, down to 1.9. But let's also presume that the rest of the world would like to achieve the same kind of lifestyle as the US, and they would probably target that level of energy use. If that happens, here's what happens. Energy use is going to grow tremendously, even under the scenario of increasing electric power efficiency by a factor of 2. We can't just do it with taxes either. Here's Jeffrey Sachs, the advisor to the governments of Peru and Russia and Poland and so on, who's a well-respected economist, the director of the Earth Institute at Columbia University. He tries to point out that we need new technologies. Taxes alone or tax policy isn't good enough. Not only that, we have to solve this problem technically in the US and OECD nations and then use that technology in the developing world if we have any hope of stopping their emissions. So that's the problem we face. I say, let's try and aim high. Let's develop a new energy source that solves many of these problems. In particular, let's try one that produces electricity cheaper than from coal. Right now, there is tremendous negotiations going on in the Congress of the United States about cap and trade. Other people are talking about maybe a straightforward carbon tax would be the most straightforward way to do that, but that looks like that's not going to happen. And the problem with cap and trade is that it has so many special interest groups that there are so many exceptions. That lesson should have been learned from Europe. Europe spent $50 billion in licenses for carbon emissions over the last few years, and their CO2 emissions went up, and most of the money went to the largest utility in Germany that burns coal. So we should take a lesson from that. I think also people are too US-centric. Just because the US cuts down its carbon emissions doesn't mean the rest of the world will. And how are we going to get China and India and those other countries to stop their carbon emissions? If we try to say, let's sign a big Kyoto treaty in Copenhagen now, they're going to say, well, wait a minute, we're willing to do that, but you know, the West emitted 350 parts per million of CO2 into the atmosphere to get where they are now, and we haven't had our turn yet. We're not responsible for that climate crisis. We want an exception until we reach your level of either carbon emissions or prosperity. I just think it's an impossible negotiating posture to take. And I don't think the Congress of the United States will agree to anything that exempts the developing world from that. The answer is to produce electricity cheaper than coal. That's a way that we can convince people from their own economic self-interest to replace the coal-burning power plants. Not only that, it means that we can produce energy cheaper than we do today, and that alone increases economic productivity. So we got two things in front of us there. And another byproduct of that is that, you know, there are many people who deny that humans are the principal cause of global warming, and many of these people are respected, and there's no need to alienate those people. Those people can also endorse a concept of more prosperous energy by having less expensive energy. When I first wrote the talk, gas was at $4 a gallon. It dropped back to $2. Synthesizing vehicle fuel in a way cheaper than oil might be an attractive a goal for a project like this. We also want it to be inexhaustible. Current rate of consumption of uranium would say 78 years worth of uranium easily available. We know that we're going to run out of oil. We've been talking about peak oil for years. We've had new natural gas discoveries, but natural gas is going to peak someday as well. People are concerned about waste. We want to reduce the waste that comes in this example from nuclear power plants, to say nothing of the amount of waste that comes from coal plants, which today amounts to almost as much as all the non-recycled municipal waste in the United States. And we want it to be affordable. Back to our goal of checking population growth in the world. It doesn't do a lot of good to try to sell $10 billion nuclear reactors to Bangladesh, but maybe if we had a $200 million reactor, we could satisfy their power needs and perhaps get a loan from the World Bank. So those are the goals. Thorium. Thorium is named after Thor, the god of thunder and lightning, and this is a play on that. Thorium is readily available. There's enough in Lemmy Pass in Idaho to power the US for a millennium. But thorium itself is not a fissionable fuel. How can it be a fuel? Let's just look for a minute at this chart. On the top row, we see the names of some of the elements, thorium through americium, and their atomic numbers, the numbers of protons in each one of those nuclei. In the rows are the numbers of nucleons, that's neutrons plus protons, it's the weight of the atom, if you will. And there are three practical fission fuels, plutonium-239, uranium-235, and uranium-233. The only one that is naturally available is U-235. The rest have all decayed away. And you probably remember that there's not much U-235 in uranium. It's decayed a lot, too. There's only 0.7% of it in natural uranium. Or just a little bit of review of what happens inside a nuclear reactor. A neutron excites a uranium-235 nucleus. It gets excited, splits into two parts. In this example, krypton and barium, and releases 3 neutrons. The total mass of the result is just a little less, and by E equals mc squared over there. That's about 160 MeV of energy. In addition, the fission products are left in a pretty excited state, so they'll decay perhaps a little more and add a little more energy to the equation. That's just for one. If you multiply by Avogadro's number, 200, which is the number of, let's say, atoms in 235 grams of uranium, you find out that it's about a ton, almost a ton of uranium or thorium required to create a gigawatt of power, thermal power. Now, let's take a look at what happens in a nuclear reactor today with the uranium-238 that's there. In natural uranium, or let's talk about enriched uranium in a nuclear power plant, perhaps 4% is U-235 and the other 96% is U-238. That U-238 on this chart absorbs a neutron and becomes U-239 for a period of time. And after a while, that naturally decays, beta decays by emitting an electron, increasing its charge, and becoming a new element, eventually becoming plutonium-239, which itself is a fissionable fuel. At the end of the fuel cycle in a nuclear reactor, after about 18 months, a third of the energy of the power plant is being generated by plutonium fission, not by uranium fission. So we're already breeding plutonium in standard light water reactors to make power. Same idea here with thorium. Thorium in a power plant can absorb a neutron, become thorium-233 that decays in 2 steps to become eventually uranium-233, which is a fissionable element that can be used to generate power. That's how that works. Those two materials, thorium-232, uranium-238, are called fertile in the lingo because they make fissionable fuels if you expose them to neutron radiation. Here's the idea of a thorium reactor. You have a fissile U-238 core just as in a normal power plant. And it's at a critical mass, so it generates neutrons that cause other uranium-233 atoms to decompose and so on. That sustains a chain reaction. In addition, there are neutrons that escape, and there's a blanket around the fissile core of, in this case, thorium-232. That thorium absorbs that neutrons, as in the examples I gave before, and it becomes a uranium-233 atom. Now, uranium and thorium are different chemical elements, so they can be separated through chemistry, not through complex isotopic separation. And you can develop a chemical separator plant that takes out the 233 fuel that has been converted and feeds it back into the uranium-233 core. In the same idea, same way, we can remove the fission products. We gave examples, I think, of krypton and barium, and there are dozens of others. You can take away the uranium and put it back and reject the fission products by the same kind of chemical process used before. So you end up with a reactor that runs pretty continuously. It's constantly replenished with thorium coming in this side and constantly emitting fission products, waste really, on the far side. And like all reactors, it generates heat that boils water or something that turns turbines to make electric power. There's a lot of innovations here. First thing is that the fuel is in a liquid form. It's not solid. Makes it easy to handle, to pump around. That liquid is a molten fluoride salt of the order of 300 degrees centigrade or so hot. It means that the chemical processing is relatively easy to accomplish. So that's innovation number one about this concept. Number two is the reactivity is inherently stable. That's because the fuel salt expands as it heats up, driving some of it out away from the critical area so that the criticality is reduced. This has another side effect. Well, the most important thing is it means the reactivity control is simple and safety controls are simplified. It also means that it can generate less than full power. So you're in a situation where you don't need all the power output, it can do load following. Today we use coal and nuclear principally for base load and use natural gas for load following. This kind of technology could do both. At the high temperature end, you can have a much more efficient conversion of thermal energy to electric power. It's not 50% using the Brayton cycle, which is used in a jet engine, compared to the about 33% efficient cycle in a typical steam plant fueled by either coal or nuclear power. Also, that high temperature enables efficient electrolysis and separation of hydrogen from water. Now, hydrogen is a poor fuel itself, but it's a good feedstock to make other fuels. And another advantage we'll come to is the radioactive waste generated by this machine would be a lot less than 1% of the waste of a current light water reactor. And in fact, can even burn some of it. How do we start one of these machines up? We don't have uranium-233 on Earth very much. It all decayed. Half-life is too short. But the US government has a lot of it. They've got 500 kilograms stored at Oak Ridge that was left over from the Manhattan Project when they were doing every darn thing they could to develop nuclear weapons. Unfortunately, that is slated for destruction by being downblended and put into nuclear power plants. And the guys who do the research are up in arms because it would be a wonderful research asset for this kind of work. But you can prime the thing with other kinds of fissile material. Any kind of fissile material can get the process started off, U-235 or plutonium, or even the leftover spent nuclear fuel from today's existing light water reactors. Eventually, all that stuff is used up and we enter the stable state of U-233. Here's, to scale, enough uranium to power a city for a year. Here's a 1-ton thorium sphere, about a ½ meter in diameter. It'll power a 1 gigawatt plant for about a year. There's about 500 gigawatts of power used in the United States. It's about $100,000 a ton, so it's not too expensive. We have in the desert 3,000 tons in storage owned by the United States government that were extracted and isolated during the Manhattan Project. And certainly at least 400,000 tons more of reserve in the United States today. So it's plentiful. A little bit of history here. Back in the Manhattan Project, Wigner developed the idea of the thorium to uranium breeder reactor. And if you look kind of at the chart, the red line at the top seems to say that you get about 2.5 neutrons out of this process per fission. The other possibility was what Fermi had proposed, and that was that the uranium to plutonium cycle worked faster because you got about 2.9 neutrons per fission, so we could make more fissile material for more weapons faster. For that reason, all the emphasis was turned towards the uranium-plutonium cycle because of the necessity of making nuclear weapons. That's not necessarily today's goal. You remember Rickover invented the atomic submarine, which could patrol under the surface of the sea for months at a time without resurfacing for refueling or running engines. The generals in the Air Force were anxious to have a similar capability for the Strategic Air Command so that they could fly bombers equipped with nuclear weapons continuously without ever having to come down for refueling. And so they promoted and funded the aircraft reactor experiment to create a nuclear reactor powered aircraft engine. That an initial experiment was done at Oak Ridge in 1954 in molten salt at that temperature. Later on, another experiment was to think about the thorium cycle, and they created a second experiment using uranium-233, which they had, and successfully ran that reactor for 4 years. They never installed the thorium breeder blanket. They instead wanted instrumentation around that reactor for their work. All that work has been captured, documented, and posted on the internet. There's a lot of information there. We're talking hundreds of millions of dollars of research at that time. Today, there are no molten salt reactors in test anywhere. But these countries, particularly France, has a group of maybe 20 people working on this project, all theoretical, all on paper. You had a speaker here from Canada, David LeBlanc, come. And you had Bonametti from US come and talk about these technologies. But people are interested. I'm just going to quickly go through some of these that establish the idea that this is just not a theoretical idea. There was a thorium reactor built, a pebble bed reactor in Germany in 1883. It was fueled with pebbles made of the fissile material U-235 and 232. It had a pressure vessel of reinforced concrete. It was a dry cooling tower, interestingly. And they had an accident of some sort. The details aren't well known. In 85, a fuel pellet lodged in the feed pipe. Apparently in Chernobyl was 88 or so, that in the work in Germany to look at radiation fallout from Chernobyl, they discovered that there was apparently radiation from a previous fuel pellet problem at the thorium reactor. People got nervous. There had been a cover-up. They shut that plant down. And of course, Germany is on a path now to shut down all its nuclear power plants. There's something called the Generation 4 Forum. They've sort of adopted 6 designs for new kind of power plants, the molten salt reactor being one of them. In a way, the forum's kind of a paper tiger. But here's the idea, again, that you have a molten fluoride salt, you have beryllium fluoride and lithium fluoride. You heat it up. It has a relatively low temperature to become molten at certain compositions, maybe 300 degrees C or so. And you can dissolve uranium fluoride in it, or plutonium fluoride, or thorium fluoride. So it's an interesting vehicle. Their design, it's just a conceptual design even, talks about how that works. An important aspect of this reactor is that it's not pressurized. It works at atmospheric pressure. So in the event of any kind of accident, there's no pressurized steam or helium gas or anything to expel any kind of radioactive products into the environment. In this example, it's graphite moderated. They estimated $1 billion R&D cost to develop this. Teller was the inventor of the hydrogen weapon. Ralph Moore was the director of Oak Ridge, and he was also the patent holder on the solid fuel nuclear power reactor. These two men, as late as 2004, just before Teller died, published a paper, again, promoting the concept of the liquid fluoride thorium molten salt reactor. India is very interested in thorium. India, remember, did not sign the non-proliferation treaty. They've been sort of an outcast, and they have not been able to buy much uranium nor technology on the open market up to now. And they have a lot of thorium. So their strategy up to now has been use heavy water reactors, reactors moderated by deuterium oxide, such as Canada developed, to convert uranium to plutonium and eventually convert thorium to uranium, because they have a lot of thorium in India. More recently, for some reason, we've signed an agreement with them to say we will send you technology and uranium. I don't understand it. It seems to undermine the non-proliferation treaty to me, but anyway, they're our friends now, I guess. India has that many heavy water reactors, 13 under construction. They are interested in thorium. They expect 30% of their electricity to come from thorium. Their technology is all involved in the solid forms of thorium. They expect to modify the existing technologies for pressurized water reactors or CANDU-like reactors for thorium. They have not adopted the concept of the liquid format. I got interested in this through this forum on the internet. There's probably 200 or 300 people on it today, Ian being one of them. And from time to time, people contributed ideas. I think there's like 30,000 posts to date. So if you have an idea and you put it up on the forum, you get a response in about an hour from somebody. What's always a mystery to me is that people like to be anonymous on these forums. I'm not quite sure why. We have a lot of mysterious, bright people we'd love to meet someday, but I don't know who they are or where they come from. So no surprise, I would recommend that we have a national project to develop the liquid fluoride thorium reactor. This is the part that nuclear engineers focus on, the reactor core and blanket. That's kind of the fun part. But there's a lot of chemistry work to be done. We finally got one or two good chemists on the forum that can perhaps help. In the uranium separator plant, that kind of work was all done in research mode at Oak Ridge 50 years ago. Similarly, the waste separation research, some of that's been done, but you have to establish a sort of industrial quality, fabricable chemical separation plants for both of those processes. These are big projects, and from an engineering point of view, you need a good heat exchanger. And part of this is will be that you may need specialized high temperature materials to achieve the efficiencies that I've been speaking about. So heat exchanger development is important. People talk about something called a triple reheat Brayton cycle, which is what's necessary to get up to that 50% efficiency. Hasn't been done with helium. There's a lot of work to be done there. In the US, companies like GE, I bet, could do a wonderful job at that. Control systems, and eventually, if we want, hydrogen separators. I gave the same talk to the American Nuclear Society last month. And this is sort of a message to engineers. It's very important to keep the costs down. And if we make cost an objective at the beginning of the project, we have a chance of achieving that. If we don't make electricity cheaper than from coal, then all those benefits I've been talking about really a lost. So you got to keep that in mind. Why can it be low cost? One is all the radioactive materials are at low pressure, so no large containment structures are needed, no large expensive containment structures. Less construction material, the negative temperature reactivity means a simple safety system. That is, as it gets hotter, the reactivity drops. There's a concept of inherent safety. What do you do if all power is lost to the plant at once and you have no control systems whatsoever? There's a design that allows a sort of a freeze plug underneath the liquid salt to melt and then drain into a non-critical shape. If we can make enough of these, we can mass produce them. And again, the fuel is cheap. We want to do it for several reasons. We want to stop global warming by producing cheap electricity. And we want also to bring prosperity to developing nations by having inexpensive power sources for them. So again, I'm proposing, just as an example, a 100 megawatt size unit. A typical power plant today is about a gigawatt. But if we're looking at under $2 a watt, we should be able to develop such a plant, hopefully, for under $200 million a unit, to make it affordable to developing nations, to allow us to distribute, to put the power sources near the points of use that cuts down on transmission line losses and makes them less vulnerable to disruption from terrorism. Let's take a look. I said, well, suppose it costs $200 million, and I kind of got my wife's HP calculator out, plugged in 8%, and here's what that would cost a month to repay the cost of capital, and if we were to divide it by the kilowatt hours produced, about 2 cents a kilowatt hour for defraying the capital cost. Again, the startup uranium is sort of expensive. This is the price that we pay today. You may not realize that we pay Russia for uranium they take out of warheads to fuel half of the nuclear power reactors in the United States today, and that's what we pay, that rate, $10 million a ton. I don't know what decommissioning is going to cost. I said half the price. Operations, I'm a proponent of low-cost operations. So the principal cost is the capital cost, as is always the case in nuclear power. Will that be cheaper than from coal? I don't know. Here's what power costs in China. These are the industrial areas of China. Costs about 7 cents a kilowatt hour. That's delivered. I don't know what it costs coming out of the power plant. In the US, we're paying 3, 4, 5 cents for distribution. So I'm guessing 3 cents will do the trick. Again, I'm suggesting we aim high, that is, use automated controls. I mean, right here in San Francisco, you get on a train at the airport that has no driver. Well, we're used to that kind of technology. Can't we do the same thing in this business? We send rovers to the moon without people, then they do a good job. Again, the idea of the inherent reactivity control makes the safety systems simple. So if anything happens to our command and control system, or we lose power somehow, the thing will decay to a stable state. And there are a lot of advantages of no workers. One is lower costs. Two is safety. You know, remember at Chernobyl, people overrode all the safety systems. People in power plants cause problems. And there's no risk of uranium theft if you have no one there to steal it. And we don't want people to be able to steal it to make weapons. I say emulate Boeing. Look at the similarity with Boeing aircraft not far from here. There's a production line. They make one a day. Boeing actually makes more than one a day, unbelievably. They're standardized units. They're able to do that. They use the newest technologies of computer-aided design manufacturing. And the units cost about $200 million each coming out the door, one a day. And they have the same concerns about life safety as the public has and the nuclear engineering community has about life safety in nuclear power plants. okay, what would happen if we were to build these things? What are the benefits? Well, let's just see what happens. Build one a week and install them to check coal power. Today we're burning 227 gigawatt years a year of coal, and we could displace all that technology with this over a period of 44 years. Faster if you wanted to build more. What about the world? I said that's a worldwide problem. Let's do the same thing, but do one a day. 1,400 gigawatt years of power used a year in the world. At a rate of one a day, we could diminish it, say, by 2058. So it will have an impact on CO2 emissions. It will have an impact on small particulate emissions. What about motor fuel? A little tougher. There is a neat process. You don't look at the diagram too hard, except to say that you heat water and sulfur as a catalyst separates oxygen, iodine separates out hydrogen, and this process works well at high temperatures, 900, 950 degrees centigrade. It's been done at a lab scale, never been done at commercial scale. There are a lot of products you can make from hydrogen. Hydrogen is a tough fuel. You can't really use it very well. But just take ammonia for a second. There are processes where you can use dissociated ammonia to fuel motors. Don't forget that ammonia is plowed into the ground to feed half the world. The Haber-Bosch ammonia fabrication process, in fact, uses more than 1% of the entire world's energy output, not just electric. And that's responsible for feeding the world. What about methanol? We got plenty of CO2 around. We can combine it with hydrogen to make methanol fuel. George Olah is a Nobel Prize-winning chemist from California who wrote the book called The Methanol Economy. And he shows the advantages of methanol. For example, it was used as a racing fuel in the Indy 500 for years and years and years. Until recently, it's being hijacked by the Midwestern farmers and so on, and they're trying to dilute it more and more with ethanol. So ethanol is a fine motor fuel. Dimethyl ether is a good substitute for diesel fuel. And I did a little, really back of the envelope suspect calculations to say it could be something like $2 a gallon to make fuel this way. So it seemed like a good idea. We ought to do it. But, there's another problem, and that is the initial power plants might not have the really high temperature materials that are needed. There's some R&D done, so we might have a little more expensive process. Let's look at oil imports for a minute. Let's make gasoline that way. Or here's the oil imports that are necessary to make gasoline in the United States. Suppose we do the same game and sell one of these a week to make gasoline. Well, it turns out we use a lot of gasoline. Over the rest of the century, we'd only cut it down by about 1 billion barrels a year. I was surprised at that. So I have to say, well, we can make it cheaper than imported oil, but that's not going to be really all the answer. A lot of the answer is what Google recommends as well, and that is electric cars. They're much, much more efficient. In this example, a Chevy Volt recharges with 8 kilowatt hours, costs about 15 cents or $1.20 altogether in New Hampshire where I live. We could power 300,000 cars on a 100 megawatt reactor. And same game, put in one a week until half of the existing 125 million fleet is replaced. And the current fleet of cars is about 20 miles per gallon. So we could knock off maybe 2 billion barrels of oil imports that way. I discovered, here's a picture of a Boeing 777. I discovered one of the reasons it's so hard to make that fuel is each one of those jet engines on that airplane is capable of generating 100 megawatts of kinetic energy. And we were only talking about a 100 megawatt electric reactor. So you can understand how these things can drink a lot of fuel. And we need that kind of a dense power source to fly airplanes. Air cooling. Typically, a power plant today evaporates perhaps 20,000 gallons a minute of water to make a gigawatt of electrical power. The advantage of the higher efficiency of thermal to electric conversion is that there's less heat rejection into the environment. And so we can get away with half of the cooling requirements of today's nuclear or coal plants. And we need air cooling in places that are arid. So instead of using water cooling, let's use a more expensive, admittedly, air cooling system. I was looking for air cooling towers, and I came across this picture of a museum in Iran. It was just so pretty. We can't make it look that pretty, but maybe you can make one that's aesthetically pleasing. And if not, look what we did in Boston. It was an ugly tower, so ugly gas tank. We just painted it. And here's a kind of a third world tower that's painted with some pictures. Now, here's what happens in a normal today's light water reactor. You start off with about 250 tons of uranium. Some of it's enriched, passed through, and about as many fission products come out as products go in. Makes sense. Most of the stuff that comes out is U-238. It's not burned up. But there's about a ton of fission products and about 0.3 tons of plutonium that come out of a typical gigawatt plant. A thorium reactor has a different mode. It only uses a ton of thorium because we burn all of it. We only burn 0.7% of the uranium that goes into one of these reactors, really. And out of this thing, we get about 0.0001 ton. We get about 100 grams of plutonium compared to 300 kilograms in the other technology. There's two reasons for this. One is that you remember that thorium-232 has a much lower atomic mass than does uranium-238. And in order to make plutonium, you need many, many more neutron absorptions successively. So the probability of making plutonium in that kind of reactor is much, much less. The second reason is that the plutonium and other such things stay in the fuel salt and in turn eventually fission, absorb a neutron, or otherwise consumed. So how do we do this? Well, I started playing games. I said, let's look at NASA's strategic plan, and this is it. Came right off their internet site, less a few adjectives. And they all seem sort of reasonable. Then I look at the last one, and part of the strategic plan is a lunar return program with utility for Mars. I'm saying to myself, gee, I bet there's money that could be redirected here. And their budget is about $18 billion a year. We're thinking a project like this might cost $1 billion over 5 years to do the R&D support. That's a very round number. That's the number that came out of the Gen 4 forum. But it isn't just the money. Look at the expertise that an outfit like NASA's got to have in materials that make sense in development of this kind of reactor. Look at the project management, the quality management skills that are necessary in NASA and a project of this sort. Probabilistic risk assessment is something that NASA used. If we said we had to be perfectly safe all the time, we never would have flown a man to the moon. They know about all this sort of thing. Energy and information technology. All these skills are important to both NASA and to this project. So I say, well, instead of going to the Mars or the moon, let's take a temporary detour and spend some of that money here. Establish a national energy program. We're not doing that now. We're trying to establish tax programs. Delay or curtail some NASA programs if necessary. And then commandeer some resources. We've got Idaho National Laboratories that built perhaps 40 of the test reactors that were built in the United States, still has a lot of capability. We've got NASA. We've got Oak Ridge that did the work on the thorium reactors, but I don't know if there's anybody left there. Argonne, and right here. There's plenty of places in this country that have skills that can be applied to a project like this. Just picking numbers sort of out of the air, saying, well, look, why do these projects take so long? Partly it's because we don't set goals that are aggressive. Suppose we say we want a 5-year goal to do all the R&D. And then at the end of that 5 years, maybe figure out how to scale it up for mass production. In the first 5 years, develop all the data and put it in the public domain. Maybe in the second 5 years, you might want the GEs, Westinghouses, and Hargraves to have proprietary products that they hope to make money on, because we want them to be able to produce one of these a day. If we produce, let's say, one a week, that's a $10 billion business. If we then start exporting these, that could be a $70 billion a year business. So there could be a financial incentive for business to do this as well. So here's the recommendation. Establish a national energy project. Commandeer resources from NASA and the national labs, and share the R&D initially, because this is a worldwide problem, but then allow commercial incentives to develop the production line to make this happen. Enjoy the benefits. I want to review for a minute. Electricity cheaper from coal from this. Vehicle fuel cheaper than oil, yes, in a long-range strategy, that's an okay objective. It is inexhaustible. We do reduce the waste. In fact, we consume waste at startup. We can make it affordable to populations of developing nations. Maybe there's a way we can achieve Meadows' goal and his model of reducing consumption in a way that population would stabilize. Maybe. I'll say right now, Meadows is not a fan of nuclear power, so I'm not trying to imply that. Thank you very much. I'd be happy for questions. I'm happy to accept questions.
You seem to ignore.
There's a mic there too, or I can speak. Go ahead.
You seem to ignore environmental impact costs to get these things through.
I ignore environmental impact costs. I've just sketched out the basic costs. That is true, but I think the environmental impact costs are less if you consider the impacts today of a coal plant or the impacts of today's nuclear power plants.
I don't mean real environmental impact. I mean fighting in courts.
Yeah, I think to make anything like this happen, you have to have a phalanx of lawyers way out in front trying to clear the path to allow such a thing to occur.
Is Stephen Chu, I believe, is the Energy Secretary. Do you have any idea if he's actually working on this or not?
Question is, do I think the Energy Secretary Chu is working on this? I think he's not.
Is he aware of it? Do you have any idea?
He has heard of me. I've written him letters. I get thank yous. I sent him the little book. But reality, no. I think the Energy Department still thinks that the right horse to ride is the liquid sodium fast breeder reactor, and their incentive seems only to be how to get rid of the nuclear waste. They don't seem to have the goals of, say, power cheaper than from coal.
So the main problem, I think, that why nuclear power fell in disfavor is how to deal with the nuclear waste. And this seems like it requires a smaller capital cost up front, but there's still no solution, no long-term solution for the nuclear waste. And especially if it was to be deployed in the scale that you were saying, although it's smaller, if there's more, then of course you would have a significant amount of waste.
Yes, the liquid thorium reactor will generate waste. All reactors generate about the same amount of fission products, which are highly radioactive for a period of years, but can be safely put aside in casks, as is now being done at nuclear power plants. Eventually, you're going to have some necessity for long-term geological storage of these materials. If we have less to dispose of, that's a big advantage. In spite of the fact that UCA is being stymied by Senator Reid, there is the existing waste isolation pilot plant in Mexico, which stores all the waste from the military programs in salt caverns that very slowly collapse and envelop the waste.
Well, I would point out that this is less than 1% of the waste increase in probable waste. There is a decrease in probable waste if you switch to something that produces 1/100th as much waste per plant. If you have 100
Not if you're- well, yeah. but-
He's pointing out that that there's less, that the 1% is less than the current plants. That is true for the long-lived waste. The immediate waste, the waste that's going to be active for 200 or 300 years, is about the same from all kinds of power plants.
and it's an insignificant fraction of the total today.
Sure.
This is also an insignificant or irrelevant comparison, I think, because we're comparing an undeveloped technology with technology of 30 or 40 years ago. Maybe if we compare this to a modern French power plant, they don't generate as much waste as our generators generate.
Okay, so the question says, am I being unfair comparing a technology from 50 years ago to a new theoretical one? Perhaps a little bit, but the facts that were given in the talk are still correct. We often look to the French as having only 37 tons of nuclear waste put aside in glassified containers every year. But you have to look more closely. The French have another 200 tons at least of the kind of waste we have, 300 tons of surplus uranium and plutonium that's not used. They have hundreds of tons of material added to their storage each and every year. They have good PR.
I was curious, you mentioned the 100 megawatt number as sort of just a ballpark, and you also talked about traditional plants are typically like a gigawatt in size. I'm just wondering, is there an economy of scale at some point in time? Like, is 100 megawatt like a really sweet point, or did you just sort of get it for some other numbers, or is a gigawatt or 10 gigawatt or whatever a better choice?
The question is the economy of scale of a gigawatt versus a 100 megawatt plant. And yes, today's plants are all gigawatt sized or bigger in the sense that the utilities put 2 or 3 of them on the same site, principally or partly because the siting permissions are so difficult to obtain. The utilities would never consider, honestly, in this day and age, try to increase the number of plant sites by a factor of 10. It would take a lot of social engineering to get people to accept that many sites for nuclear power plants. Now, the other thing is that the engineers do say, too, well, wait a minute, economies of scale here, Bob. We can make 1 gigawatt electric turbine less expensively than 100 megawatt turbines. And perhaps that's right, but that forgets about the fact that if you have a production environment where you have competitive suppliers and rapid turnover on the production line, there are economies that occur as the technologies develop that I depend upon in this idea to happen.
Why is thorium commonly talked about in liquid fuel reactors rather than uranium-238?
Why thorium instead of uranium-238? Uranium-238 is, in fact, a reasonable fuel. We have a lot of it. There's even been experience in Chicago with the integral fast reactor. The advantages of thorium are that it works how can I say? The advantage of thorium is more plentiful to begin with. Another thing is that it generates much, much less of plutonium and other high-level wastes and material that could be used for other purposes. But I don't know that there's a liquid fuel design for a uranium-238 reactor. There are a lot of compromise designs. I only showed just one that people deal with that would involve other fuels in addition to thorium.
Let's thank our speaker. Let's thank our speaker again.